Welcome to Dungeon Academics. My name is Thomas and I will be your instructor. I'd like to talk about dice today from a purely mathematical viewpoint. As players of games, dice is something that we use very frequently, and I think it's worth having a bit of knowledge about the background and the maths behind them. I've done lots of videos where I go into sort of algebra, averages, frequency distributions. This video, I'm actually talking about the shape of the dice themselves. And I'm hoping there might be something interesting and new that you can learn here today. So let's start out with our standard dice. If you buy a set of basic D&D or RPG polyhedral dice, it will come in a set of 7 dice normally. These include your D4, 4-sided dice, your D6. Now, when most people who aren't hardcore roleplay game nerds talk about dice, they exclusively mean 6-sided dice, D6. You've also got your 8-sided dice. You have 2 10-sided dice. You have a regular 10-sided dice, which is labelled 1 through 9 plus a 0, which represents the 10. And then you'll have a percentile dice. Let's see if I can get this to focus. Come on. There we go. Yep. Which is labelled in the 10s. 10 all the way through 90 plus 1 face, represented with 0, 0. Now, there has been some debate in the community about how to read these dice, and I have heard people try to argue that if you were to roll a 10 on the percentile dice and a 0 on the regular dice, because that's a 10 plus 10, that should be read as 20. I think most people disagree and would read 10 and 0 as 10, and most of the roleplay game rule mechanics that I've read instruct you to do this. This dice simply represents the 10s, and this dice represents the units, the only exception being if you roll 0, 0 and 0, that counts as 100. That's the way I run it. And if I ever in a situation where I have to write my own rulebook, that's definitely how I'm going to include it. There are more, larger versions of these dice that have hundreds and potentially thousands on. I think it's possible to create a D10,000. Well, theoretically, you can go as far as you want with each dice representing one larger in place value. But percentiles, 0 to 100 are the standard ones. You've also got your D12, and finally, especially important for Dungeons and Dragons players, your D20. Now, the majority of these dice are what we call Platonic solids. Plato was a Greek philosopher a couple of thousand years ago, and he wrote a treatise associating the 5 Platonic solids with different elements in the universe. And this is back when they still had earth, air, fire, water as their principal elements. Now, 5 Platonic solids, I've just shown you 7 dice. 2 of those are not Platonic solids. Now let's get into what that is. Firstly, we need to understand what a regular polygon is. A polygon is a 2-dimensional shape with straight edges and a convex shape. A convex shape means you can pick any 2 corners of a shape, draw a line between them, and that line will either be on the edge of the shape or inside the shape. There are no divots cut out of the polygon. Everything is facing outwards. So your regular shapes, triangle, square, hexagon, these are considered regular polygons. You can make irregular hexagons. Let's not go there though. Now, a Platonic solid, a regular dice, is a 3-dimensional shape with a regular polygon as its face. Let's take your standard D6. It's a 3-dimensional shape and it's made up of 6 squares joined together. So it forms a regular cube. Each face is the same shape, and it's put together in a way that it is also a convex shape. You can connect any 2 corners of this dice with a line, and that line will either go along the edge or along the face of the shape or through the middle of the shape. At no point will this connecting line be in the air. This means that all the faces are, I want to say face outwards, but that's not quite the right word. If you imagine a little cave cut into the shape, you would end up with a face or set of faces that the dice couldn't actually land on. I mean, it could land so that the mouth of that cave was down, but the faces inside the cave couldn't actually be rolled. So this is a convex polyhedra. Polyhedra meaning a three-dimensional shape. Now, if we look at our standard dice, let's start with a D4. This is what we call a tetrahedron. It's got 4 sides made up of equilateral triangles. So each face is an identical triangle, 4 of them stuck together. That's your D4. The cube, as I said, 6 faces, they're squares. You've got your D8. This is what we call an octahedron. It's made up of 8 equilateral triangles. So it's the same triangles that make up the D4, but stuck together in a different way. 8 of them. Moving up, we have the D12, the dodecahedron. This is made of 5 pentagons stuck together, and it forms a very pleasing shape. I'd actually like to say, as a mathematician, D12s are my favourite dice, because 12 is a very easy number to do maths with. It can be divided by 1, obviously any number can, but it can also be divided by 2, 3, 4 and 6 and itself. We don't have to worry about that. Because 12 can be split up into lots of different numbers, it's very easy to do fractions with. D20, on the other hand, can be, well, let's say it's also made up of triangles. It's made up of 20 triangles stuck together, and it's called an icosahedron. 20 is not as good a number to do maths with as 12. It can be divided by 2, 3, 4, 5, and 10. And sure, that's a lot of numbers, but 20 is also a lot bigger than 12. 12 has more factors for its size. Now, that leaves us with D10s. D10s are not regular polyhedra. They're not Platonic solids, because each face, if I put this here to focus on it, each face is a kite. There are 2 pairs of sides with the same length, a longer pair and a shorter pair. And because of that, it's not a regular polygon, so it's not a Platonic solid. We include 2 of them in the set, but it's the only one that's not a Platonic solid. Now, there was another mathematician called Euclid, who's often considered the father of geometry. He proved that these 5 Platonic solids, the D4, the D6, the D8, the D12, and the D20, are the only ones that can exist. There are no others hidden in 3-dimensional space. I have to specify 3-dimensional space because I have personally no idea about 4-dimensional polyhedra. This is not an area that I studied. I studied university, physics at university. There are probably going to be mathematicians out there who say, well, yeah, if you have 4-dimensional dice, we can make all of these lovely dice. But we're 3-dimensional creatures, so let's just stick with the Platonic solids for now. Just also to note, the reason the D10 is included, even though it is not a Platonic solid, is because in general we use a base 10 counting system. And we use a base 10 counting system because we have 10 fingers. So you count to 10 and then you make a mark and then you start again. That's a base 10 counting system. As we use base 10, it makes sense to have a base 10 dice. I've just argued that base 12 would be easier, and I will tell you now for free that if by some genetic miracle humans were born with 6 fingers instead of 10, we would use a base 12 counting system and our mathematics would be easier. There are some places that use a base 20 counting system. French, for example, is what they call a vigesimal, a base 20 counting system. The way you count numbers is you count multiples of 20 plus something else. The same can be said for Danish. 8,5 is Danish for 58. It's 8 plus half. Oh, sorry, did I say 58? half thrice. No, that would be 78. It's Danish for 8 plus half more than 3 lots of 20. Half more than 3 is 3.5 times 20, 70 plus the 8, 78. Danish. And before we get too weird, English is partially base 20. 407 years ago. 407, 408, I don't know the Lincoln's Gettysburg Address, but a score is 20. We have that word built into our language. So 20 has always been an important number for counting, and it happens to be the largest of the Platonic solids. I like dice. Now you know what a Platonic solid is. I hope you like dice as well, but I want to show you something interesting. If I asked you to roll 2d6, I'll get some out just for comparison. Standard 2d6. I'm fairly sure that most of you would know how the results of that are likely to lie. You're probably going to get something about 7. 6, 7 or 8 has about a 50% chance of coming up when you roll 2d6. You know that 2 and 12 are the most extreme answers and also the least likely answers. And you probably have an understanding that if you were to roll 2d6 lots of times, you would get a probability distribution that looks a bit like a pyramid, with a peak with 7 being the most common and at the edges 2 and 12 being the least common results. What if I gave you these 2 dice instead? Now, you should right away tell that these are not standard dice because this bottom dice has 2 faces of 2. In fact, it has 1 face of 1, 2 faces of 2, 2 faces of 3, and 1 face of 4. So 1, 2, 2, 3, 3, 4. This dice, on the other hand, is also not a standard dice. It has faces of 1, 3, 4, 5, 6, and 8. Now, what's interesting about these 2 dice is that when rolled together and added up, they are indistinguishable from these 2 dice. If I told you to go into a room, if I went into a room and I rolled these dice 100 times and I noted down the results, and then I rolled these dice 100 times and noted down the results, and I showed you both set of results, you would not be able to tell which was which. The probability distribution for this pair of dice, called Sicherman Dice, I hope I'm pronouncing that right, is identical to this. If we made a map of all the 36 possible different results on these 2 dice, 6 faces on the first, 6 faces on the second, 36 overall, there is 1 possibility to roll a 2, 2 possibilities to roll a 3, 3 possibilities to roll a 4, so on and so forth, all the way to 2 possibilities to roll an 11 and 1 possibility to roll a 12. It is identical to the frequency distribution map for 2 standard D6. If you are playing a game of Catan, where the only thing you do with the dice is you roll them and add the scores together, this would give exactly the same game with exactly the same odds as 2 standard dice. That's all it does, though. It doesn't work for anything else. In Monopoly, for example, when you roll 2 dice to see how far you move, if you roll a double, you get another turn. And you have a 1 in 6 chance of rolling a double on 2 normal dice. You have a 1 in 9 chance of rolling a double on this. So if doubles count, these dice are now different. If you have a reroll, for example, Great Weapon Fighting in the 2014 version of Dungeons & Dragons lets you reroll damage dice of 1 and 2. You get different result distributions with these once you start throwing in rerolls. They only work if all you're doing is adding the 2 values together, and then they are indistinguishable. And what makes this interesting is that it has been proven that these are the only 2 dice that can replace 2d6 if you agree that the faces have to be natural numbers. By that I mean whole positive numbers excluding 0. As a side note, there is a slight debate in the mathematical community about whether 0 should be considered a natural number. In some arguments, it should. In some arguments, it shouldn't. I'm specifying here no blank faces. So natural numbers starting at 1. There are other pairs of dice that you can make that can replace 2d6 if you're willing to have negative values, blank faces, or even fractions and decimals on the dice. But if you want every face to have a number, every face to be positive, and every face to be a whole number, this is the only way you can replace 2d6. Now, I really like this as a gimmick. I would play Catan with these dice, and I'd have to persuade everyone sat around the table that it's identical, and I'd have to explain out to everyone at the table that there is no benefit whatsoever to doing this apart from the fact that I think it's fun. So that might be a hard sell, you know. Let me persuade you with a 20-minute maths lesson to do something that is no benefit other than the fact that it amuses me. Well, I've got a YouTube channel about Dungeons and Dragons maths, so obviously I'm the kind of person that would do that anyway. But I like stuff like this. I like unusual dice. I have quite a few games that use specialist dice. So for example, let me just grab this from here. These are my dice for the Alien RPG from Free League. And they are standard D6s, but they just have a different symbol on 6 because there's the stress mechanic. I play Necromunda. Necromunda's a lovely little game from Games Workshop, and it uses a fairly standard set of D6s. There's nothing unusual about that, except that it has your house symbol for the number 1. Come on, focus. There we go. No, it's the number 6, I apologise. But it also comes with a random direction dice. It's called a scatter dice. There's a hit, and there's a random direction. And you have injury dice, dead, wounded, flesh wound, and you have a wonderful thing called a sustained fire dice. It tells you how many shots an automatic weapon gets. 1, 2, 3, or the worst one, only 1, and check for ammo. Now, dice have 2 uses in games like this. You can roll the dice to get a random value, or you can use it as a marker, as a token that has 6 sides. So it's a way of generating a random result or showing a specific result. And I like games that use dice in unusual ways. I particularly like roleplay games with dice pool mechanics. I think dice pool mechanics are a great innovation, and the Star Wars roleplay game from Fantasy Flight Games has one of the best dice mechanics using custom dice. Now, I don't think Dungeons and Dragons should move to custom dice. I think Dungeons and Dragons has a legacy of using standard polyhedra, and that legacy is an important thing to preserve. But by understanding how dice work, we can do more with them. There are lots of neat little mechanics you can use in-game that use standard dice. The older version of Great Weapon Master, which I mentioned before, gives you a reroll on a certain value. There are some mechanics that give you additional dice if you roll a double. I think it's Chromatic Orb gets another blast off if you roll a double on your dice. And if you upcast it high enough so that you're rolling 6 dice, then you automatically get a double because there's only 6 possible results. Oh, sorry, 7 dice. You need 7 dice to automatically get a double. And having neat little things you can do with dice in your game, I think are fun. I think there's a lot you can do just by being imaginative with your dice rolls and understanding that little tweaks, how you do rerolls, how you gain extra dice. If you understand the mathematics behind them, you can improve your game. But anyway, that was my brief introduction to polyhedral dice. I hope there was something in there that you found new or interesting. I recommend everyone check these out. They're called Sicherman Dice. I'll spell that in the description for the video so you know what to Google for. And if you have any questions, please do put them in the comments. Thank you for listening to me talk about dice, and enjoy your next game, whatever it may be.